Welcome. Today, we're diving into the fascinating world of heart metabolism, especially under stress. When the human heart faces failure or injury, its energy needs and sources shift dramatically. One molecule, beta-hydroxybutyrate, or beta-OBE, has emerged as a key player in this metabolic adaptation. But is it a friend or foe? In this video, we'll explore how beta-OBE acts as both an alternative fuel and a signaling molecule, and what this means for heart health, especially during heart failure and other cardiac stresses. The human heart is a powerhouse, circulating about 7 tons of blood daily and producing nearly 6 kilograms of ATP, almost 12 times its own weight. Under normal conditions, the heart relies mostly on fatty acids for energy, with glucose, lactate, and ketone bodies like beta-OBE contributing smaller amounts. But when stress strikes, such as in heart failure or during ischemic events, the heart's fuel preferences can change. This metabolic flexibility is crucial for survival, allowing the heart to adapt to different energy demands and substrate availability. Ketone bodies are small molecules produced mainly in the liver, especially when fatty acid and carbohydrate supplies are low. The two main ketone bodies used by the heart are acetoacetate and beta-hydroxybutyrate beta-OBE. In a normal fed state, ketone levels are low, but they rise significantly during fasting, prolonged exercise, or a ketogenic diet. In certain diseases, like diabetes or heart failure, ketone metabolism changes, and the heart may rely more on these molecules for energy. When the heart is under stress, such as during heart failure, it adapts by increasing its use of beta-OBE as a fuel. This shift is an early response to maintain ATP production when fatty acid oxidation is reduced. Studies show that in advanced heart failure, the heart's reliance on ketone bodies can rise from less than 10% to over 20%. This adaptation helps the heart keep up with its energy demands, especially when other fuel sources are limited. In healthy adults, circulating ketone body concentrations are around 50 μm. However, during fasting, exercise, or ketogenic diets, levels can rise to 18 μm in pathological conditions like diabetic ketoacidosis. They may soar up to 20 μm. These changes reflect the body's metabolic state and can have significant implications for heart health, especially in disease states where ketone metabolism is altered. The heart is one of the body's top consumers of ketone bodies, especially when other fuels are scarce. Both beta-OBE and acetoacetate are used, but beta-OBE is more sensitive to stress. The ratio of beta-OBE to acetoacetate reflects the mitochondrial redox state. Interestingly, high acetoacetate levels have been linked to worse outcomes in heart failure, while beta-OBE appears to be more beneficial, making it a focus for therapeutic research. Animal studies have shown that increasing beta-OBE can protect the heart from injury. For example, fasting or exogenous beta-OBE delivery before ischemia reperfusion injury reduces infarct size and improves heart function in rodents. These benefits are linked to enhanced energy production, reduced oxidative stress, and improved mitochondrial function. However, the timing and amount of beta-OBE are crucial, as too much or prolonged exposure can be harmful. In humans, heart failure is often accompanied by metabolic changes, including increased ketone body utilization. Both diabetic and non-diabetic patients with severe heart failure show higher beta-OBE use, which correlates with disease severity. Delivering beta-OBE to patients with reduced ejection fraction has been shown to improve cardiac output, suggesting potential therapeutic benefits. However, the effects in patients with preserved ejection fraction are still under investigation. Lifestyle interventions like fasting, exercise, and certain diets can raise beta-OBE levels. Studies show that intermittent fasting or fasting-mimicking diets may reduce risk factors for aging and cardiovascular diseases, partly by increasing beta-OBE. However, long-term ketogenic diets may have negative effects, such as impaired glucose tolerance and cardiac fibrosis in rodents. Thus, moderation and timing are key when using lifestyle to influence ketone levels. Not all increases in beta-OBE are beneficial. In some cases, such as prolonged exposure or very high levels, beta-OBE can be detrimental. For example, it may alter glucose uptake, increase oxidative stress, and even promote cardiac fibrosis. In certain heart diseases, elevated beta-OBE may predict worse outcomes. This highlights the importance of understanding the context, dose, and timing when considering beta-OBE as a therapy. Beyond its role as an energy source, beta-OBE acts as a signaling molecule. It can inhibit histone deacetylases, HDACs, leading to increased acetylation of histones and other proteins. This affects gene expression, mitochondrial function, and cellular metabolism. Beta-OBE also reduces the production of reactive oxygen species, ROS, and promotes autophagy, helping cells cope with stress and maintain homeostasis. Let's visualize how ketone bodies are produced and used. In the liver, fatty acid oxidation leads to the creation of beta-OBE, which is then transported to the heart. There, beta-OBE is converted to acetoacetate by BDH1, and then to acetyl-CoA by SCOT, entering the TCA cycle for energy. This process is tightly regulated and essential during metabolic stress. Histone deacetylases, or HDACs, are enzymes that regulate gene expression by modifying histones. In heart failure and other stresses, HDAC activity is often increased, contributing to disease progression. Beta-OBE acts as a natural HDAC inhibitor, increasing histone acetylation and altering gene transcription. This can lead to protective effects, such as enhanced autophagy and reduced inflammation in heart cells. Autophagy is the process by which cells recycle damaged components, especially important in heart cells under stress. Beta-OBE can stimulate autophagy and mitophagy, helping remove damaged mitochondria and reduce oxidative stress. This supports mitochondrial health and may protect the heart during ischemic injury or heart failure. Inflammation is a key factor in heart disease. Beta-OBE inhibits the NLRP3 inflammasome, a protein complex that triggers inflammation. By reducing NLRP3 activity, beta-OBE can lower the production of inflammatory cytokines and help protect the heart from injury. This anti-inflammatory effect adds another layer to beta-OBE's cardioprotective actions. Beta-OBE also acts as a ligand for certain G-protein-coupled receptors, GPRs, influencing fat metabolism and sympathetic nervous system activity. It can promote anti-atherosclerotic and anti-inflammatory effects through these pathways. Additionally, beta-OBE can modify proteins and histones through acetylation and beta-hydroxybutyrylation, further impacting gene expression and cellular function. SGLT2 inhibitors are diabetes medications that also benefit heart health. They increase beta-OBE production by promoting ketogenesis, which may partly explain their cardiovascular benefits. Clinical trials show that SGLT2 inhibitors reduce heart failure risk and improve outcomes in both diabetic and non-diabetic patients, possibly through mild, sustained increases in beta-OBE. Given its benefits, several strategies have been developed to deliver beta-OBE therapeutically. These include intravenous infusions, oral ketone esters, and supplements like 1,3-butanediol or medium-chain triglycerides. Early studies suggest that these approaches can improve heart function and metabolic health, but more research is needed to determine the safest and most effective ways to use beta-OBE in patients. Let's summarize beta-OBE's protective mechanisms in the heart. It acts as an alternative fuel, inhibits HDACs, reduces ROS, promotes autophagy, and suppresses inflammation via NLRP3 inhibition. These combined effects help the heart adapt to stress and may improve outcomes in heart failure and ischemic injury. Despite promising results, many questions remain. Not all ways of increasing beta-OBE are equally effective, and the best timing, dose, and delivery method are still unclear. High or prolonged beta-OBE exposure may be harmful. More research is needed to fully understand how to harness beta-OBE's benefits while minimizing risks, especially in different types of heart disease. In summary, beta-OBE is a fascinating molecule with the potential to both help and harm the heart, depending on the context. As an alternative fuel and signaling molecule, it offers new avenues for therapy in heart failure and other cardiac stresses. However, careful consideration of dose, timing, and patient condition is essential. Ongoing research will help clarify how to best use beta-OBE for heart health, opening the door to safer and more effective treatments in the future.